And God said, "Let there be light." And there was light. Light is so natural to us and so important for our everyday lives. We use light for vision, for energy, and it gives us magnificent landscapes, like the northern lights. For a scientist, light is indispensable. Almost everything we know about nature comes from seeing something. Today, I will give you a tiny glimpse on what happens at the exact moment when light is born. We know that light is a form of energy, and it comes from many different sources. Heat, like the sun, electricity, like the lamps above us, chemistry, like a glow stick that shines when we break it, and even living organisms, like the glowing fireflies. When light is emitted or created, it takes some energy from the emitter, the sun, the glow stick, the lamp. But why do we care so much about the moment when light is emitted? Well, the answer is that the better we understand this moment, the process, the better we can use light for our own purposes. Controlling light, this art, is the heart of modern technologies. We count on sunlight for fueling our energy demands. We use light for communication worldwide. We use light detectors like cameras for photography and for medical devices. And we use powerful lasers for science, research, defense, medicine, everything. Although all of these technologies are very advanced and very mature, we still have a long way to go. The main challenge that outstands all the potential and the challenges in this field is actually to emit light faster, meaning emitting the same amount of light just in shorter time. This makes light brighter and more precise, and it actually improves a lot of our everyday technologies. So it can make our X-ray scans better, it can make navigation of autonomous cars in crowded areas better, and it can even improve the accuracy of satellite-based navigation. To improve the light sources and to make the light emit faster, we need to meddle in just the right moment, exactly the moment when light is born. So let's first see how naturally light is emitted. We know that light is energy. Something converts this energy from something to light. The converter is the atom, the smallest piece of matter. It takes some energy in some way, holds it and processes it, and then emits it. The thing that is emitted is the photon, the smallest piece of light. This process is almost instantaneous. It can happen like 1 billion times per second, but it does take time that we want to shorten. Now, to see how, let's use an analogy. Emitting light is like baking a cake. The baker gets a bag of ingredients, holds it, processes it, and then bakes the cake. And our goal is to decrease the time the baker takes to bake a cake. More cakes, less time. So what's the problem? Bakers are artists. You cannot control them, you cannot tell them what to do. They just bake you cake at some constant rate. We could hire more of them, but we get stuck along the way. It's not the right solution. What we do want to do is to shape their environment. We want to optimize the bakery. Optimizing the bakery means that each cake takes less time to be baked. So how it's done? The baseline level, the thing we'll compare to, is that for one baker, one bag of ingredients gets you one cake in 1 hour. In terms of light emission, this is the baseline level of emission. When we have 2 bakers, each bag of ingredients gets you 1 cake in 1 hour, so that's 2 cakes in 1 hour. In terms of light emission, it is twice as bright, twice the light, same amount of time. But this is for independent bakers. What if we could make them cooperate? If they could cooperate, they could do the same job of baking 2 cakes in half the time. In terms of light emission, it would be 4 times as bright, because it's twice the amount of light in half the amount of time. Okay, sounds promising, but what do we need to do? In order to create this cooperation, we need basically 3 things. Let's hold on to the analogy of the bakery for a little longer. We need the bakers to be closed, but not too close, or they'll step on each other's toes. We need them to be team players, and it's not trivial that they will cooperate. And we need the cooperation to be so strong that it overcomes any personal differences and crises and conflicts and whatever. If we manage to do all of this, we have a super bakery. Likewise, in atoms and light, we have the same conditions. If the atoms are closed, it's good, but they don't want to be close enough, or they bond and become a molecule. We don't want that. They need to be team players, and it's very, very specific types of atoms that are able to do it. And the cooperation needs to be strong enough to overcome any imperfections and disorder and non-uniformity and any undesired effect. If we manage to do that, we'll get a superradiance. Radius like radiation, same amount of light in shorter time. And this is actually a term. So what is superradiance? Actually, it's quite a standard today, in the sense that if I have a physical system, and I want to demonstrate that I have good control over it, in the distancing of the atoms and the cooperation of the atoms, what I do is that I demonstrate superradiance. The problem is that I require really, really specific conditions for it to happen. The two essentials one are exotic materials, the team players, and really cold temperature. The intuition behind this is that even if you take team players and you warm them up a bit, they get angrier, jiggle around, and they just don't cooperate. So we need really cold temperatures. Now, for this reason, I don't have a superradiance flashlight in my pocket. It's not something that is close to happen. A recent breakthrough, however, showed that superradiance can occur in slightly warmer temperature. Not something in my pocket, but in the right direction. The exciting part is that we're not really sure why, in the sense that our theory and the predictions do not predict such strong cooperation in warmer temperature. Now, this is where my research comes in. We take these exotic materials, which are becoming more and more common, which is good for my pocket, and we take them in warmer temperature. We look at the emission. We investigate any sign of shortening of emission time or any other more complicated evidence. And we look for a model, both theory and experiment, that captures this exact cooperation, why it happens and how can we use it. Now, our current lead is that this cooperation is unique in the sense that it's not only strong, but long distance. And this is how these materials are able to overcome any imperfections and the warmer temperatures. We believe that this mechanism that we're still trying to grasp will be able to get us all the way from warmer temperatures to much warmer temperatures. So I still need a fridge for my flashlight, but it will be near my pocket. Now, this would be amazing because these light sources would be much more efficient and much brighter than any other source. And what I ask you to do in the next time you turn on the light in your home, just imagine how many photons and atoms jiggle around when you do it, and how much just a little cooperation could do the difference. Thank you for your attention.